So the next idea that we are going to be talking about is errors. And errors are always going to be part of any experiment in science. No one can claim of an experiment which is completely free of errors. And if not completely eliminating the errors, we can at least aim to minimize their impact on the readings. And for that, it's important to understand the different types of errors that we have, because we also deal with these errors differently. So let's go on and talk about these types of errors. So as was written above, we can say that errors are of two types, which is systematic. So systematic versus random errors. So here we have systematic, here we have random errors. Now we'll be talking about examples in just a bit, but first let's just give a general categorization of what these types of errors are really. So with systematic errors, the idea is this. Systematic errors are basically due to faults in either the apparatus or in the experimental procedure. So how we are carrying out the experiment, it could either be a problem with that or something with if something is wrong with the apparatus itself. On the other hand, random errors are basically errors due to external conditions. And again, this will be more clear when we actually talk about examples of systematic and random errors. Now, if you look at both of these, you can also see that systematic errors we can sort of get rid of completely as well. But random errors, because this is due to external conditions and it basically causes fluctuations in the readings, we cannot entirely ever get rid of these. So systematic errors either causes the readings to be or less or more than the actual value. And what this means is, for example, if I'm taking a reading and it's supposed to turn out to be 10, and the readings that I'm getting, maybe with systematic errors, it could always be like 11 or 11.1 or 11.2. So it's always more, right? And again, these do not necessarily have to be by the same amount. So not necessarily by the same amount. Right? You could also have, for example, if you're using a meter or something, and it could also be that the error is in such a way that maybe it causes the needle to be sticky, and maybe it introduces a percentage based error. So maybe it causes the reading to be 5% more than it is actually, right? So in that case, it's not necessarily by the same amount, but the idea is that it either causes all readings to be more, or it causes all readings to be less than whatever the true actual value is. In contrast, when we talk about random errors, this causes a scatter, or we can say it causes some fluctuations about the true value. Now, for example, if I continue with whatever that we were talking about, let's say I was expecting a value of 10. So with the random error, what is going to happen is that sometimes I would get values of like 9.8, 10.2, 9.2, 10.8, so that sort of thing. So it's fluctuating about the actual value, which is 10. None of these are as important as what I'm going to write now, which is basically how do we deal with these types of errors. So you might know of this idea of from O levels or whatever level you did earlier as well, that whenever we can, we do try to repeat readings because it basically reduces the impact of errors. And when we talk about averaging, especially averaging with respect to either type of errors, the idea is this, that these types of errors, which are basically systematic in nature, these cannot be reduced by averaging. So how do you then get rid of these? These can only be rectified by improving the experimental practices. Now what do I mean by this? This will now become clear in just a minute. By improving experimental practices or the experimental procedure. Whereas when we talk about the random errors, so this can be reduced by averaging. We'll also be talking about line of best fit in a while. So you know that basically how we make the line of best fit. We try to get the line as close as possible to the points that is linked to this here. So let's say if I have a grid like this, y and x, and maybe my points look like this. So like this, this. And when I try to make the line of best fit, I try to have the line so that it is as close as possible to most of the points. So this is basically the effect that averaging has on the data points. So because it's usually scattered, even drawing the line of best fit, which we will do when we are talking about practicals, that's also a way to reduce random errors. Now on to examples of some of these. Now again, I'm doing the same thing, the examples of systematic errors here on the left, examples of random errors here on the right. So for systematic errors, some examples. So one of the most common ones is zero error. Basically, if you have a clock which is, for example, running 5 minutes ahead of time, or another clock which is running 10 minutes behind of time, these are examples of zero error. So basically your reading is always shifted by a certain amount. And if you think about this, this always makes the reading more or less than what it actually is. So zero error is a type of systematic error. And even if you are trying to average it out, it makes sense that the average would also be shifted by that same amount. So you cannot get rid of zero error by averaging. How can you get rid of it? Is, for example, you guys must be familiar with the idea of a micrometer. Used to be in the AS syllabus, isn't part of the syllabus anymore. But basically with the micrometer, how you can remove the zero error is just to see what it is and to subtract it, right? Similarly, talking about parallax error, which is basically caused by incorrect viewing positions, is also a type of systematic error if the following scenario is basically in place. So let's say I'm reading of the volume which is there in a measuring cylinder, and I'm always looking at the level from below. Then in case this would basically classify as a systematic error. But this is also sort of like a gray area, because if I'm sometimes looking at this from below, sometimes looking at this from the top, then this would also classify as a random error. But with the way that things stand right now, if I'm always looking at this from below, I would say this is a type of systematic error. So sometimes you might be reading a textbook or something, and somewhere you might see that somebody has called this a random error. Some may have called this a systematic error. So this is the reason behind it. Now if you talk about like more concrete examples actually related to an experiment, then if we talk about measuring the time period of oscillation of a pendulum, then wrongly timing the oscillations, this would also classify as a systematic error. And to understand this idea, what I'm talking about is basically this, that let's say this is what our pendulum looks like, and with this being the mass which is basically oscillating. Now let's say if I say that one complete oscillation is maybe only this much when it goes to a position like this. Now this is obviously wrong, because this is not one full oscillation. One full oscillation would be when it goes here and then comes back here. Right, so something like this, or wrongly placing a meter rule whenever you're measuring a length, that would also basically fall under the category of a zero error in a way. So these are all examples of systematic errors. On the other hand, if we talk about examples of random errors, one of these is human reaction, which is a pretty general one. So any place, for example, if you have to operate some machinery by yourself, let's say you have to start and stop a stopwatch, then that would have human reaction time involved in it, and that would basically classify as a random error, because sometimes I might start it a bit early, sometimes I might start it a bit late. So in that case, the fluctuation could be either more or less, and it's not either always more or it's not always less, so it isn't systematic errors. And with human reaction time, you know that how we can basically reduce the role that human reaction time has. For example, if I'm talking about the same idea of timing the oscillations of a pendulum, then I can time more oscillations, and I can time more oscillations multiple times, and then I can average out those times. So that is a way that you can reduce the impact of random errors in your readings. Apart from that, other ones are, again, it's more according to the experiment we're actually doing. Let's say, for example, if you're making something, and let's even make this a non-science example. Let's say you're making coffee and you're using a measuring scale. When you place the same amount of coffee, it might show you like 7 grams of coffee on one measuring. Then another one, it might show you 7 again. Maybe on the third one, it shows you 8. Right? So these are some fluctuations that will happen. Maybe if you have your fan turned on, and that would also like interfere with the reading. So that can also cause the reading to fluctuate. Right? So any sort of error which causes readings to fluctuate, all of these would be classified as random errors.
Quick pause. If you're finding value in this explanation, there's so much more to discover at Alt Academy, where we break down every A-level concept with the same clarity. Now back to the video lesson.
Now in turn, when we talk about systematic and random errors, both of these lead to 2 more measures that we use regarding our readings that we get using a certain experiment. So if we talk about systematic errors, as we were doing on the left, so systematic errors basically relate to the idea of accuracy, and random errors these relate to the idea of precision. Now, what do each of these terms in turn mean? Let's talk about this first. So accuracy. So as we just discussed, systematic errors cause our readings to be more or less than the true value. So then the idea of accuracy actually relates to that when we're taking measurements, we have some idea of a ballpark where our readings would lie. So accuracy is the name of this measure, that how close are the measured values to the true or the actual value. And on the other hand, if we talk about precision, so we know it introduces scatter in the experiment in our readings. So when we talk about precision, this is basically how close the measured values are to each other. Right? So if you have a value, if for example we did an experiment which had very little systematic error, then this means that the actual values, the measured values, would be pretty close to the true value. If we did a experiment which had very little randomness or random error, we would say that the measured values would be very close to one another because there would be very little scatter. There could also be cases where the readings are accurate but not where the readings are accurate but not precise, could be precise but not accurate. Either it could also be that both of these are true, that the readings are accurate and precise, and it could also be that the readings are neither accurate nor precise. So for this, let's do a few examples to basically understand how such cases could arise. Let's say I'm doing an experiment to find small g on Earth. This experiment will also come up later in kinematics, and I know that this value, and this is also something you're supposed to use in AS, that is 9.81 meter per second square. So I'm doing a reading, I'm doing an experiment to find out the small g of Earth. this is the value I would be expecting. And in each of the cases, I'm now going to write down the values that I actually got. So for this, I found out small g of earth. And let's say this is also a standard in AS. This you'll learn when you'll start doing labs. It's a standard to have a minimum of 6 readings whenever you do any experiment. So I'm going to write 6 readings here, and then we'll talk about accuracy and precision of this experiment. So let's say using this experiment, the 6 sets of values that I got, maybe they look like this. So 9.70, 11.30, maybe even like 12.50, and just making these up as I go along. The last one is, let's say this is a 6th one, right? Yeah, so this is maybe like 10.90. So 10.90. All right. Now we'll be talking about whether this set of values, whether this is accurate or precise or not. So first of all, if I want to talk about whether this is accurate, I can see there are this is like an entire set of values. So to talk about accuracy, let's first find out the average G value here. Because I have 6 readings here, I'll just add all of these up. So I'll sum them up. This is just the Greek symbol for sum, divided by the number of readings, which in this case are 6. So the average value for small g turns out to be 9.85. So if I look at the actual value 9.81, what I'm getting is 9.85. So this is fairly close to the actual value. So I would say yes, this is accurate. But if I look at the values within itself, there's a lot of spread. The smallest value being 6.9, the largest value being 12.5. So the max value is almost double of whatever the smallest value was. And because of that scatter, I'm going to say this is not precise. Right? So this is a type of reading which is accurate but not precise. Now, whenever questions come, they might ask you this either in terms of a bullseye or in terms of this graph. Let's just first look at the bullseye because I know you guys hate graphs. So in terms of a bullseye, let's say these are some 6 values that I got. And again, how I'm placing them does not really indicate anything significant. But I can see that if I just average these out, so they are all, basically if I average these 2 out, that would be somewhere along the center. Average of these would be somewhere along the center. Average of these would be somewhere along the center. So I've just used that to show that it's accurate. But because each of the darts that I've thrown are fairly far away from each other, so I would say it is not very precise as a reading. Now what's the graph? Now you also need to be familiar with this graph. On the y-axis I have number of readings, and here I've marked the actual true value. So this is my true value in this case, which is 9.81. So I can see that my most of the readings, the way that they average out, these are fairly close to the true value because the value I was expecting was 9.81. This is 9.85. So this is pretty easy to see. But because each of the readings are like fairly scattered, they're fairly spread apart. So in this case, my graph would look something like this. So this value being very close to this means that this is accurate, but because the graph is like very well spread out, so this is not precise. Let's go on to the next one. Let's have some more values to work with. Now let's say somebody else does the same experiment and they get a different pair of values. So the small g values that they obtain, those look maybe like this. right? So these are the couple of values that they get. So these are what their 6 values look like. Now if I again find out the average of these, so G average in this case, again just adding all of these up and dividing by 6. Again, because I just made these values up, and I can also see this from the data, the average would be somewhere between 6.7 and 6.8. So actually this average is turning out to be 6.765. This is also something you will study in practicals, is that if all of this is given to 2 decimal places, your average should also be to the same accuracy. So this is 6.765, so 6.77, right? So if I talk about this, is the average value in this case, is this close enough to the actual value, which is 9.81? And the answer to that is no. That's why this is not accurate. But if I talk about precision, this would be precise because all the values are fluctuating within the vicinity of 6.7 and 6.8. So this would be precise. Now again, if I just show you the same ideas on the bullseye and on the graph. So with the bullseye, I can see that my readings are not very fluctuated. So all of these are within some sort of ballpark, but it's actually very far away from whatever the true value is supposed to be. So this being the actual true value. So it's pretty far away from that. If I again show you the same idea on this graph of the number of readings versus the actual values that we get. So our value that we get, the average is not very close to the true value. So maybe that's somewhere around here. But most of the values are within, again, the ballpark. So there's very less spread. So this is a very precise reading, which is why it's going to have a very sharp peak as well. Now compare this to the previous one where we had a much flatter and broader peak. Moving on. So let's place the bullseye and the graph beforehand. And let's say small g of Earth in another experiment. This I get as so this is 4, let's say, right? So these are the values that I got. Again, let's find the average G value. So average turns out to be 9.80, which is fairly close to the actual value that I was expecting, 9.81. So I would say this is accurate. And if I look at the readings within themselves, they're also very close, again in the vicinity of 9.7 and 9.8. So I would say this is also precise. So on the bullseye, I would say that my values are very close to the actual value, right? So there's which is why they're basically averaging around the center, and they're also not very farly spaced apart. And for the graph, I would say that the most of the readings are very close to the true value, and there's also very little spread. So this graph would be again narrow because it is precise, and here because this is a accurate value. So this is the case of readings which are both accurate and precise. Let's go on to the last one, and you can now probably guess this for yourself as well. So let's say the set of values in this fourth case, that looks like this. So maybe small g of Earth values look like alright, so maybe this is what the values look like. So 4.7, 3.85, 12.7, 8.5, 5.6 and 9.10. Again, just first finding out the average G value. So the average value turns out to be 7.408, so 7.41. So it is far apart from the actual value of 9.81. And there's also a lot of spread within the values itself, the smallest being 3.85, the largest being 12.70. So this is the case of a reading which is neither accurate nor precise. So again, on the bullseye, these would be readings which are all over the place. Right, so these are neither accurate nor precise. They aren't like centered around the actual value, and they're also pretty far apart themselves. And on the graph, this is not close to the true value, so the peak would be somewhere around here, and it's also very spread apart. So the values in this case would look something like this, right? So it's very further spread apart as well. So maybe like this and this. So that's all of the ideas regarding precision, accuracy, systematic, and random errors.
Hey there! If you found this A-level physics lecture helpful, why don't you head over to altacademy.org and sign up for the full A-level physics course. You can sign up for physics, chemistry, biology, math, or 4 other A-level subjects. Thousands of students have already taken the leap. What are you waiting for? See you there.